Hello everyone. On this video we will be going over infinite limits. Okay, so we're going to start off with a general definition. Okay, so what if we let f of x be a defined function for every real number in an open interval. Okay. Now we say that open interval contains some value c, and it's real for every value. Okay, so in an open interval, let's say you have some value a, some value b, and there's some c right in the middle. Or it doesn't have to be in the middle, it can just be in between a and b. Okay, and that function is defined everywhere, and it could be or it may not be defined at c. Okay, so let's say except possibly at x equals c. Okay, so it's defined everywhere, maybe not at c. Okay, so that means the statement the limit of f of x as x approaches c is equal to infinity just means that for any, let's say, uppercase m greater than 0. And we use uppercase because we're saying this could be a really big number. There exists an f of x that's bigger than that number, than that really big number. So, really big number. Okay, so no matter how big of a number you can think of, there's always going to be an f of x value or an x value that you can plug in that'll be bigger than that. And that's how you know your limit of f of x is infinity. Okay, so let me kind of draw it out for you to help you visualize it. Okay, so let's say we have our x and y axis, and straighten that out a little bit. My y axis was a little crooked. Good enough. Hopefully you get the idea. Okay, so you have your x, you have your y axis. Okay, so in some interval, let's say you have some c value. Now let's say it doesn't exist at c. Okay, so we know that x can't equal c. So if you have some f of x value, as it gets closer to c, your f of x just get bigger. Now let's say on this side, same thing. As it gets closer to c, your f of x value just keeps getting bigger and bigger and bigger. Okay. So really what they're saying is, no matter where you place m, you could place m at 1,000,000, 1,000,000,000, so f of x equals some really big number, you'll always go past it. Okay, you'll always find an f of x value that will be bigger than whatever m you can think of. Alright, so this is for infinity. Let's look at negative infinity. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to the next portion. There we go. Alright, move paper on down. Okay, so now, once again, we're going to let f of x be a defined function for every real number in an open interval containing c, except possibly at x equals c. Okay, so it's the same stipulation as the limit the limit is equal to infinity. Okay, now the statement, move that up a little bit, the limit of f of x as x approaches c equals negative infinity in this case. You can make sure that's filled in. There we go. Just means for any, let's say n is less than 0. In this case, this just represents a really small number. There exists an f of x less than that really small number. Alright, so let's go ahead and draw that. Okay, so let's say this is your x and y axis. So that's your x, and that's your y. And I purposely drew it shorter up there. Okay, and again, let's say you have your x equals c value, that it's undefined at that value. Okay, so what we're saying is, as your f of x gets closer and closer to c from the right, the number just keeps getting smaller and smaller and smaller. And as x approaches c from the left, again, it just keeps getting smaller and smaller and smaller, non-stop. Okay, so basically, no matter what value you can pick negative 1 million, negative 1 billion, doesn't matter. Your f of x is equal to whatever this n value is. That means there will still exist an f of x that will be less than that n value, no matter which one you pick. Oh, move that up some. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to the properties of infinite limits. Whoops. There we go. Okay. So we'll look at properties of infinite limits. Oh, I already erased that one. There we go. Alright, so in this case, what if we let C and our uppercase L be real numbers? And what if we let f and g represent functions such that, I'll just put st for such that, say the limit of f of x as x approaches c equals infinity, and the limit of g of x as x approaches c actually has a numerical limit value. So we'll let that equal L. Now, that period there. Alright, so one, we'll look at the sum or the difference, or basically adding and subtracting. Okay, so let's say the limit of f of x, either plus or minus because they're both the same, g of x as x approaches c is going to be infinity. Let me clean up my infinity a little bit. Okay, so that means if you add a limit that has a function, that has a limit, or a limit, you find a limit with an actual limit, and you find a limit with an infinite limit, if you add them together, it's just going to be an infinite limit. That's like saying this, if you have a limit here that's 4, if you have infinity plus 4, it's still going to be infinity. So that's why if you add those two together, it's just going to be infinity. Alright, so move that up a little. Second, we're going to look at the product. Okay, so let's say if you have the limit of f of x times g of x as x approaches c. That's going to equal infinity, but only if that limit is positive. So if that limit is greater than 0. So if you get basically a positive limit times infinity, it's still going to be positive infinity. But if you have the limit as x approaches c of f of x times g of x, it is possible for it to equal negative infinity. But that's only if that limit is less than 0 or just negative. Okay, so if you have a limit of -7 and you multiply that times a positive infinity, it's going to be basically a negative times a positive, which is negative. Okay, here, if your limit is positive, positive times a positive is going to be positive. Okay, so it's the same thing if you have a negative infinity times a positive number, then that's going to be negative times positive, which is negative. And if you have a negative infinity times a negative limit, negative and negative is going to be positive. So it's the basic multiplication rules. Alright, so the third, if we're looking at the quotient, let me kind of separate these a little bit. There we go. So if you have the limit as x approaches c of g of x over f of x, okay, these aren't interchangeable. You have g of x, which is your actual numerical limit, over infinity, or a limit of infinity, then that is actually going to equal 0. Okay, you're probably wondering why. Okay, so if you have a limit here in your numerator, let's say the limit of that is 4. Just pick one. I'll just write this out here. So if you have a limit in your numerator of 4, and let's say this limit just keeps getting bigger and bigger and bigger. So you have 4 over 1,000. But this number just keep getting bigger. So eventually it's going to be 4 over 1 million. And eventually it's going to be 4 over 100 million. And eventually that's going to be 4 over 100 trillion. Oh, 100, I said 100 billion since I'm running out of room. Okay. Now, if you notice, if this is approaching infinity and this number has a limit of 4, then no matter what, it's just getting closer and closer and closer to 0. Okay, so if you plug all these into a calculator, 4 out of 1,000, 4 over a million, 4 over 1 million, 4 over 100 million, 4 over 100 billion. It's just getting smaller and smaller and smaller and smaller. Okay, so it's eventually going to get really, 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 really close to 0. It'll never hit 0, but it will get really, really, really close to 0. All right. So if you are still writing, feel free to press pause. Oh, actually, let me put one little note here. All of these are really similar for one-sided limits also. For one-sided limits and negative infinity. Okay, so the rules are pretty much the same. If you apply all of these, x approaches c from the left or right, same thing. All right, now, if you're still writing, feel free to press pause. But we're going to go ahead and move on to our first example. Before we get started on our first example, another little side note. Let's say the limit of f of x as x approaches c equals, let's say, either positive or negative infinity. Okay. It doesn't mean the limit exists. It does not mean the limit exists. Okay, it's actually saying the limit does not exist. Oh, I'm out of pencil lead here. Let me. Alright. There we go. It is saying the limit does not exist. Oh, there we go. Or in most cases, does not exist. D and E. Okay, so if your limit as x approaches c is positive or negative infinity, then you don't have a limit. It does not exist. All right, now let's jump into our first example. So what if we want to find the limits? Okay, so let's say for problem A, the limit as x approaches 2 from the left of 3 over x minus 2. And let's say for problem B, the limit x approaches x approaches 2 from the right of 3 over x minus 2. Okay, so both the same function, but we're approaching it from the left and from the right. Okay, so let's go ahead and start problem A. Okay, so remember, we're approaching 2 from the left, so we're approaching it this way. That means this, at some point, we're going to cross 1. Okay, so we have the limit of 3 over x minus 2 as x approaches 2 from the left. Let's go ahead and get a little table going. Okay, so since we're approaching 2 from the left, I'll put the 2 over here. Okay, so 2, and that's a little question mark. And that's your x. And that's your f of x. Okay, so let's say if we plug in x equals 1.5, let's say 1.9, and if you wanted, you could have started right at 1.9, 1.99, 1.99, etc. So let's say 1.99 and 1.99999. Okay, so if you plug in x equals 1.5, you'll actually end up with -6. If you plug in x equals 1.9, because remember, we're going 1.5, 1.9, 1.99, 1.99999, and so closer and closer and closer to 2. You plug in 1.9, you get -30. You plug in 1.99, you get -300. You plug in 1.99999, you get -300,000. And you see it's getting smaller and smaller and smaller. F of x is getting smaller as x approaches 2 from the left. Alright, so since x is getting infinitely smaller the closer we get to 2 from the left, then that means the limit of 3 over x minus 2 as x approaches 2 from the left is equal to -infinity. Alright, so have that one down. Let's go ahead and tackle B. Alright, so if we have the limit of 3 over x minus 2 as x approaches 2 from the right. Okay, now remember, we're approaching 2 from the right. So if you have 2 here, at some point it's going to be 3, and you're approaching 2 from that way. Okay, so we'll go ahead and create our table. Move it over a little further. Okay, so we have our x and our f of x. Okay, so we're approaching 2 from the right, so we'll put 2 here and our little question mark there. Okay, so what if we put in 2.5? Because remember, we're coming this way, so 2.5 is about there. Then we get a little closer, let's say 2.1. Okay, let's say 2.01. And 2.001. And 2.00001. So we're getting closer and closer and closer to 2. Okay, so if we plug in 2.5, we'll end up with 6. We plug in 2.1, we'll end up with 30. Plug in 2.01, we end up with 300. We plug in 2.001, we end up with 3,000. If we plug in 2.00001, we end up with 300,000. Okay, now you see here, your f of x is actually getting bigger as x approaches 2 from the right. Is getting bigger as x approaches 2 from the right. Okay, so if you see that it's getting bigger and bigger and bigger, so as you get closer and closer to 2, we can see that the limit, I'm about to put f of x, oh my goodness, of 3 over x minus 2. 3 over x minus 2 as x approaches 2 from the right is going to equal infinity. Alright, so you want a quick graph as to how this would look. Actually, I'm going to put that on the next page instead of trying to squeeze it in that one little corner. I'll continue that on the next page. So if you are still writing, feel free to press pause. But I'm going to go ahead and show you how the graph would look on the next page. There we go. Alright, so just to show you the graph. Okay, so let's say if we have our x and y axis. There we go. So we have our x and we have our y. Okay, we know that x cannot equal 2. So you see here that it gets closer to 2 from the right. It's going to approach infinity. Limit of 3 over x minus 2 as x approaches 2 from the right. Remember, that's going to equal infinity. But as it approaches 2 from the left, it's going to go towards negative infinity. 3 over x minus 2 as x approaches 2 from the left. Okay, so this is going to equal infinity, and this is going to equal negative infinity. Alright, so if you are still writing this one, feel free to press pause. But I'm going to go ahead and move on to our next example. Alright, so let's say, for example, we want to find the limit and that is the limit as x approaches 1/2 of x times secant of x. No, actually make secant pi x. Kind of change that up a little bit. Alright. So, to solve this, it's very helpful to remember that secant pi x is equal to 1 over cosine pi x. Okay, and since we have cosine of pi x, if we plug in that 1/2, so that's pi times 1/2, which is just cosine pi over 2, which is equal to 0, we can't use direct substitution. So we can't use direct substitution. Okay, so since we can't use direct substitution, we have to do a little bit of work to solve it. Alright, so say the limit as x approaches 1/2 from the left. Okay, because we know that in order for the limit to exist, it has to be the same from either the left side or the right side. Okay, so that's of x secant pi x. Remember, secant pi x is 1 over cosine pi x is equal to the limit as x approaches 1/2 from the left. That's x times 1 over cosine pi x is just x over cosine pi x. Okay, now if you set up your table like we did previously, and you just get closer and closer and closer, you set up the, let's say 1/2, remember 1/2 is the same as 0.5. So we're just going to approach it closer and closer from this direction. So if you plug in 0.1, 0.2, 0.3, 0.4, 0.5, you'll find that your limit just keeps getting bigger and bigger. So your limit is actually infinity. Okay, so now let's try it from the right. So the limit of x secant pi x as x approaches 1/2, but this time from the right. Oh, made that a little bit too big. Let me kind of edit it a little. There we go. Okay, so this time we're approaching it from the right. Let me separate that a little bit. There we go. Now, once again, the limit as x approaches 1/2 from the right, replace that secant, so that's x over cosine pi x. Now this time, using our trusty number line, remember 1/2 is just 0.5, and we're approaching that from the right. Okay, so we can say 0.51, 0.501, 0.5001, 0.50001. We can get closer and closer and closer to 0.5 from the right. Okay, now if you do that, creating the table, you'll see it gets smaller and smaller. So it approaches negative infinity. Okay, so you can see here that the limit approaching from the left is not the same as the limit approaching from the right. Okay, so that means the limit of x secant pi x as x approaches 1/2 does not exist. Or just a good old-fashioned B&E. Okay, so since, just a little edit, as x approaches 1/2 from the left does not equal the limit as x approaches 1/2 from the right. Okay, that's the reason why it does not exist. If they were equal, if this was infinity and this was infinity, then your answer would be infinity. If this was negative infinity and this was negative infinity, then your answer would be negative infinity. But since there are two different limits, the actual limit at that particular point does not exist. Alright, so hopefully that made sense, and I will see you on the next video.